This is a rather smart-looking little USB power supply. It's a bench supply made by Yihua, and it's called the Yihua 502D USB, and it's got the two terminals in the front, the moving coil meter, and the USB output and the power switch. On the back, it says input voltage 220 to 240 volts AC. They might do a lower voltage version, and rated current 1 amp, which is a bit disappointing that it's 1 amp when it actually goes up to 2 amps, but maybe it's just the continuously rated 1 amp. It's also got a fuse in the back. Let's take a look at the fuse. Is it going to be a ceramic? No, it's going to be a glass fuse, but it's better than nothing. Gives it that sort of professional look. So let's test this. I'll just take that cover off. It does have the CE label, but as we've come to expect, CE doesn't mean Certificate of European Conformity or whatever it is. It actually means caveat emptor in the case of these products. Buyer beware. So let's plug this in. No bang, that's a good start. Okay, let's test this. I could use this. I'm going to say also that this is a 2-pin. It's very light, so it's obviously a switch mode power supply. It probably, I should test that right now. Hold on. Let's see what the voltage with respect to ground is. So I shall turn this down to, where am I going here? Where am I going here? AC volts. And we'll just probe the outputs. That is turned on. I'm having to be careful here because this is so sloppy, this plug. I should change the plug, in fact, for a British one. So let's test the leakage voltage by just stuffing this into a random terminal and going to earth. 91 volts. That's the sort of the coupling you get. This is a common thing with even a standard, even a good quality. Say, for instance, this Motorola power supply. It's a USB power supply. It's not earthed, so there is going to be some coupling from the main side to the outputs. This would experience that same thing. And it's definitely not like one of these power supplies where you just don't know what is being coupled across. So just out of interest, what current would that be? Let's put it to the milliamps microamp setting. It's not going to be high, though I say that there could be quite a loud pop here if it is. And I shall go from the output to earth. It's only about 200 microamps. But you know, the 90 volts, 200 microamps, it could upset some delicate circuitry or make it behave quite oddly. It's not like a traditional power supply. Let's put that back to the normal setting. You know, I could use this to measure the... Hold on. I'm going to get the crocodile clips and put them onto this and some bits of wire, and we'll actually treat it as a little bench supply. So I'll put this out of the way. Get the crocodile clips in, or alligator clips. Plug them in, and we'll set it up to the 20 volt range. And I'll get a couple of bits of wire. There's a couple that'll do. Strip that. And I shall wrap these around these terminals. So it's got this sort of binding post type terminals that you can clamp a wire in. I should have wrapped that right round, but I didn't. And you can also push the banana lead in. That's where a banana to banana would have been quite good. Banana. Da, 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 da. But I don't have banana to banana. And my apologies for MD who recognises what I just the banana. Da, 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 da. You're going to have that stuck in your head all night now. Right, a Muppet tune. Let's connect up and see what voltage we get here. That's not very impressive. 4.7, okay. Maybe it'll go up under load. Let's tuck the wire down like that, shove this in here, and ramp that up. So that's us at half an amp, 4.67 volts, not quite the 5 volts. Let's go up to an amp. 4.63 volts, also quite low. Let's go up to 1.5 amps. 4.6. Will it go all the way up to 2? Oh, it goes right off the scale. And then it's, oh, look at that. Look at, it is cutting out and it's trying to reboot, so to speak. So let's turn it down to 2 amps. 4.5 at 2 amps. 4.6 at 1 amp. It's not exactly a 5 volt supply, is it? That's a bit odd. I wonder if that's adjustable. Let's open it up. So I've unplugged it. Let's get the back off it. I'll just put this meter out the way at the moment. So it's got 2 crosshead screws, and they're not too deep. Yeah, that's not a great start. I was kind of hoping for actual 5 volts. I'm missing another screw here, or... oh no, there it goes. Oh, it's quite neat inside. I was actually expecting something like a module out of a sort of generic power supply like this to be tucked inside, but it does look like it's got a dedicated supply in there. The mains lead has come into this. The cable has been tied in a knot and then glued. It's been sort of slit and stripped back, but they've just left the outer sleeve on it. That's a bit shoddy. The blue is going to the fuse. It's going to the end connection of the fuse, and then it's coming back up. It's coming via the switch. So the switch in the front is switching the mains, and then it's coming to this connector here. Let's see if we can get this power supply module out then. It does a filtering. That's quite nice, and a fusible resistor. Is this going to be glued in? Try not to damage it. Oh no, it's coming out. It's coming out. Seems to be quite a tight fit. So what do we have? Ooh. Oh, we've got quite a modest anti-tracking gap there. It's not got the typical, the sort of triple insulated wire type of thing. It is just a traditional transformer, which I'm not sure how good that's going to be. Let's get in close to this. Is this image bright enough? Should I brighten it up? This is where it all goes horribly wrong. No, that'll do. So what do we have? We have the main supply coming in, goes through this fusible resistor. There is a common mode suppression choke. Then there's a bridge rectifier. Then there's the smoothing capacitor. There's the chip with the diode. There's the bootstrap circuitry. Resistor, capacitor, diode. That's the filter, the snubber network for the windings. It's got a class, what looks like a proper class Y capacitor there. Very common arrangement for this chip, that it's got the optocoupler coming back, and then there's a little capacitor in the vicinity of that. That's probably part of the feedback circuit. The TL431 is what they've used on this side. Hold on, let's just double check that is a TL431, but that is the classic 431. So the thing that's deciding the accuracy of that voltage is the resistors they've chosen here, and they've just not quite selected the right ones to put out 5 volts, because otherwise it should be a fairly rock solid 5 volts there. The output goes through a single generously rated diode. Then there's a capacitor. The capacitor has a little resistor across it for stability and to ensure it discharges quickly. That's fundamentally it. It really is just, it's Opto Isolator, the voltage detector circuit based on the TL431, which is a sort of voltage threshold detector. It's a programmable shunt that will light the LED in that, and then it's signalling back to this chip. Lots of soda around there. They really are. They've taken it fairly serious. They've got a separation slot there as well, and under the chip. The chip itself is called, it's actually quite clearly marked, it's at top 222PN, top 222PN. So, yeah, that's kind of a shame that they've, that just purely because of the resistors in here, and I don't have much in the way of surface mount resistors to try and tweak this. That's disappointing. I suppose I could use ordinary resistors, but that would be a whole load of faffing about. It would be nice if there'd been a little potentiometer here just to tweak that. It's actually got 2 connectors out here. 2 connectors. Oh, you know what? You know what? One of those connectors is part of the feedback circuit. It looks as though it may have had the facility to actually tweak the voltage via a front panel adjuster. but they've capped it off just with the standard components in there. The front of the circuit board has the USB output, but it's got some resistors here to set a potential difference on the data lines, which will indicate to anything plugged into it that, you know, it can probably put out at least 1 amp. They haven't just bridged them together though. They have used resistors. I wonder what current they're aiming at. I wonder what appliances would charge if they were plugged into it. So that voltage, it was about, was it 4.6 volts? It's not far off 5. It's not ideal. But it would have been nice if it had been a rock solid 5. But other than that, what is there to say? It seems, I wonder how hot it gets in use. There's one way to find out, and that's take a thermal camera to load it up. One moment, please. So yes, this video turned out longer than expected because when I did the thermal imaging scan, well, for a start, the hottest component predictably is the diode, and at 1 amp the diode got up to about 49 degrees Celsius. At 2 amps it went to 90 degrees Celsius. That's pretty normal in these things. The chip itself is quite a highly rated chip. It's rated for quite a lot of current, so it went to 44 degrees Celsius at 1 amp, 57 degrees Celsius at 2 amps. So to be honest, I'd say the power supply is really rated for about the 2 amp mark. But rather disconcertingly, the other hot component that it shouldn't be hot is the Opto Isolator. I'm sure I've come across this before. And the Opto Isolator was at 50 degrees Celsius at 1 amp and 60 degrees Celsius at 2 amps. And you think, that's really hot for an Opto Isolator. And I took a look at the circuitry. I thought, is that coming from the primary side of the Opto Isolator, the LED side, or is that coming from the secondary side? So I measured, there was a resistor here, which in this case was 270 ohms, and it had 0.9 volts across it in normal operation. Now, if you divide the 0.9 volts by, let's 0.9 volts, I equals V over R, so that's 0.9 divided by the 270 ohm resistance, gives you 3 milliamps, 0.003 amps. So the 3 milliamps is not going to make that hot. So it's not in the LED side, the output side. The other side seems to be following the correct topology of the schematic. It's got the diode and the capacitor, and it's got the, hold on, let's unplug it, bring it over. It's got the little diode in there, and this is a capacitor here, this green one, and they're all correct place. Now it's got this capacitor down here, the only slight difference being it's got a resistor in series with it. But the current, I'm guessing the current flowing into the control pin is what's making that hot. But it shouldn't be hot. It shouldn't be that high, I wouldn't have thought. The data sheet didn't indicate there was going to be excessive, you know, levels of current. It's very odd. I'm not sure. Unless the voltage from this winding is actually too high. I really don't know why that is getting so hot. Kind of puts me off this a little bit, because an Opto Isolator should normally be completely stone cold. That's very strange. I don't know why that is. So the only real things I can say about this, another thing that's notable, the cores are all very, very loose, both in the suppression choke here, the COM mode suppression choke, and the main one. It's actually very loose. The component values could be adjusted. I wonder if you could work out from the TL431 type component if that was designed to take the potentiometer to adjust the output up and down, maybe trim it, or just maybe it was designed to be a variable voltage supply. Everything else kind of looks okay. It's just that thing that's niggling me is how hot that Opto is getting, and there's no real reason for it, because it seems to be following the design properly. I do wonder if the winding ratio and the transformer's perhaps not correct. It seems very strange. But yeah, mixed thoughts now. Just that Opto is just like really throwing me off this. It's not really, I don't like that aspect of it. I'm so used to Optos being cold. Other than that, it would have been quite nice. More so if it had put the 5 volts out, but I have to say, it might have its own, it might have some applications, but I'm not actually over enamoured by that, so I think I'll give this one a thumbs down. I'm not giving up that easily. I decided to try and nudge the voltage up, and the way I did that, I connected a couple of connections to this connector that I thought maybe for a sort of front panel knob, and you can adjust it to quite a modest voltage. But by putting 47k in, I was able to nudge the voltage up to just over 5 volts, and it has to be over 5 volts because it does drop when you load it down. The other thing that's worth mentioning while we're looking closer at this circuit board is this chip here. Although it's an 8-pin chip, there are 6 of the pins are just blobbed together in the back. And the reason for that is that it's basically a MOSFET inside. That's the source, and it's for heat sinking. And all it requires is this control pin here. Actually, that's just, my fingers are far too big. So this is the source that's all common together to dissipate the heat. This is the control pin, and that's the drain, which is going to the actual transformer, to the primary transformer. And it turns out the Opto Isolator may actually be part of the circuitry in a rather weird way. It's being used for multiple things to keep that pin count down. If you, I could actually read this out, but it would be quite boring because yeah, I'll try and explain it instead, pictorially. When you turn the power on to this, current flows from the drain through the sensor input, the control input, and it charges up this capacitor. So once that capacitor reaches the threshold at which this will operate, the circuit starts up and the unit starts driving the transformer. But to keep that capacitor charged up, it's almost like the bootstrap type system. As soon as the output reaches the desired voltage, and this is also a safety feature because if you overload it, it actually effectively turns itself off. It's quite neat that way. But as soon as the voltage reaches, in this case, 5 volts, and the regulator circuit starts conducting and the LED turns on the Opto Isolator, the Opto Isolator then connects the power supply, which is this diode and capacitor here. It connects the output of that to the control pin, and that not only provides the feedback to the control pin, but it also charges this capacitor up to the sort of maximum level. And the maximum level is set by a shunt circuit in here that as soon as the voltage across that capacitor is high enough, it shunts it to the source connection here. So basically speaking, it relies on that Opto Isolator turning on and off to actually provide power to the chip. And I'm guessing that the voltage that's from here is ultimately going to determine how much power is dissipated in the Opto Isolator. Quite a lot in this case. So maybe, I'm sure I've come across this before, a Opto Isolator, and it possibly was that. So let's take these out of the way at the moment. Let's brighten the image up just a tad. That's far too much, but that's okay. Let's bring this back in and plug it back in, making sure it is unplugged first to avoid any awkward moments and hysterical screaming. So let's put this back on here. The low voltage connection on here. Let's bring in the more chunky tester. I'll just put that little note out the way. Let's bring this in and the load unit. And making sure that everything's completely clear, let's turn this on. So now, can you see this? It's showing 5.25 volts on the unit here. And as I increase the load, let's take it up to 1 amp. I should be looking at the dial on the front here. It's so much easier. That'll do. Yep. 1 amp, the voltage has dropped to 5 volts. I think 5.2 to about 5 is acceptable. If you go beyond that, if you go up to the 2 amp region, let's look at the dial here because it's so much easier than waiting for the digital readout to catch up. It drops to about 4.9. So you know what? Once that slight tweak is applied, it actually becomes quite usable because it is putting out the full 5 volts. Even if it does mean that off load, with no current being drawn, the voltage does creep up to about 5.25 volts. Interesting. You can go up a lot higher and then it starts tripping the protection. So I'll run it right up to the top and you may even hear it. The voltage has just plummeted. And I can hear it going tap, 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 tap. Don't know if you can hear that. And that's it just trying to restart. And as soon as the current demand is down, it can get its supply again. And all that's happening there is because I'm overloading it, the voltage is never reaching the point on this. Oh, that's just swamping out horribly now. Let's shove this out of the way. Let's take the exposure off and nudge that down. What's happening there is because I've overloaded it and the voltage is so low, that opto isolator is never turning on, so it's not providing the current to that. So what's happening is that this capacitor is discharging to the point this cuts off, and then it starts the cycle again. It slowly charges this capacitor up through the circuitry, has a go at trying to drive the output. If it can't drive the output, it shuts down again. But if it can drive the output and reach its destination voltage, then it will start powering itself. In a way, that's quite clever. Suddenly, I've warmed to the circuitry, even if the opto isolator is warm too. So, that does make me wonder then. The only other test I'd like to try in this is the high voltage insulation test. I really should do that, shouldn't I? One moment, please. Okay, that's us set up. Let's see what happens. I've got it set to the 2 kV setting. Let's ramp the voltage up and see what I've done here. By the way, I've connected the 2 input terminals together onto one leg of the tester and the 2 output onto the other leg. So the voltage across the circuit board, the main thing I'll be testing is the transformer, the isolation. So let's start ramping this up and see what we get. So that's 280 volts, 300 volts. The current, it's going to trip in that current because this is set to 1 milliamp trip roughly. So that's 1 kV. I think I've set to 1 milliamp. It's trip. That is because it's got a fairly generous class Y capacitor, I think. So let's set this up to 2 milliamp trip current, and let's try that again. So let's ramp it up from, let's get up to 600 volts, 700 volts, 800 volts, 900 volts, 1000 volts, 1500 volts, 2000 volts. So that's effectively 2000 volts. Let's bump it up a wee bit further, see what we can go to. Oh, it's gone back down again. Oh, of course, it's limited, so it won't go up beyond 2000 volts. Okay, so that passed its test. Up to 2000 volts AC, which is going to be higher peak DC voltage, well, the peak AC voltage. So yeah, that's all right. 2000 volts. Okay, that's reassuring. So in summary, it would be very nice if the unit actually came out set to 5 volts out the factory. They could have actually just put a trimmer there, or they could have tweaked it in the factory and put a resistor across those terminals just to nudge it to the 5 volt area. But other than that, it's quite generously rated. If you look at the case, let's get this thing out of the way here. If I can get this back off. Let's get the little unit back up again. If you look at the case, it's got the ventilation louvers underneath. It's got the unit mounted vertically inside, and then it's got the ventilation slots out the top. So now we've ascertained that it can be tweaked to actually put out 5 volts. I do like the fact it's got the display in the front. I think we may have actually saved this. I think we may have saved grace here. It's fused in the neutral, which is a bit naughty. Goodness knows what the cable is. And it is capable of doing 2 amps for periods of time. I'd say probably continuously, but you know they rate at 1 amp. And you can tweak the voltage. So yeah, it's gone from being a thumbs down to being a, it's okay, it's tolerable.